Watch a robot grab an object in midair. It looks graceful, effortless, but beneath that physical motion is an invisible, chaotic web of software fighting to keep the machine from crashing into itself. When people want to build machines like this, they usually ask, what is the best language to learn for robot programming? That question assumes robot programming is a single, unified discipline. This graphic shows the reality. Robotics is a highly fragmented, layered stack of abstractions. You have to choose exactly where you want to live in the stack. At the very bottom, you are manipulating bare metal voltages. This layer is purely about physical force, sending electrical signals directly to motors and actuators to make them turn. Moving up, you hit microcontrollers and embedded logic. Here, software acts as the nervous system, calculating exactly how much power each motor needs, while middleware orchestrates the messages between different parts of the machine. At the very top, you have high-level perception and AI. This is where the robot processes camera feeds, identifies objects, and makes complex decisions about what to do next. If you commit to the wrong entry point, you will waste hundreds of hours. You will end up fighting low-level hardware bugs when you actually want to build AI. Or you will write brilliant AI code that reacts far too slowly to safely operate a physical machine. Mastering robotics requires matching the right software stack to the specific problem you want to solve. If your goal is making robots smart, Python is the default starting line. Python gives you instant access to massive, pre-built libraries for computer vision and machine learning. You can write a script to identify a human or map a room in an afternoon without waiting for complex code to compile. But Python is an interpreted language. The system has to translate your code on the fly, which introduces milliseconds of overhead latency. In a purely digital environment, a few milliseconds rarely matter. But if a heavy robotic arm reacts too slowly to a sensor detecting a human in its path, that latency becomes dangerous. To test these high-level ideas safely, engineers often turn to simulation tools like MATLAB and Simulink. These environments let you design and verify complex control algorithms with high fidelity before touching any physical hardware. The cost of that safety is expensive licensing, and you still have to eventually translate your simulated algorithms into executable code for deployment. Living in the prototyping stack means accepting a compromise. You gain massive cognitive capability, but you sacrifice execution speed and hardware efficiency. Down at the embedded hardware level, reaction times must be instantaneous. This is the domain of C and C++. If you want to control physical actuators, these languages are mandatory. This chart compares execution speeds. Because C and C++ are compiled languages offering direct memory management, the code executes with zero latency, real-time precision. That speed is what allows a robot to safely calculate motor torque, manage battery loads, and physically balance itself 1,000 times per second. The cost of this performance is a steep learning curve. C++ syntax is unforgiving compared to Python. If you make a mistake, you aren't just reading a simple error message. You are hunting down obscure memory leaks that require deep technical expertise to fix. The performance stack throws away the comfort of rapid prototyping to guarantee absolute deterministic control over the physical machine. So how does a high-level Python brain talk to the low-level C++ muscle? If you build everything from scratch, you'd spend years writing custom drivers just to get a camera to talk to a motor. The solution is the Robot Operating System, or ROS. It functions as a middleware orchestrator. This network graph shows how ROS abstracts the underlying hardware. It breaks the robot's functions into independent programs called nodes, allowing them to pass messages to each other over a network. A vision node written in Python can identify an object and publish its coordinates. A motor node written in C++ can immediately grab that coordinate message and drive the wheels to that exact location. But ROS carries heavy operational overhead. It requires a robust operating system, usually Linux, just to run the background network. Because of this heavy footprint, trying to run ROS on a simple microcontroller or a basic hobbyist board will completely overwhelm the processor. ROS solves the fragmentation of robot programming, but it acts as a resource-hungry bridge that is only justified when you are building complex, multi-sensor systems. If you step away from custom development and walk onto a factory floor, the rules change entirely. In industrial manufacturing, integrators often rely on online programming. Operators use handheld devices called teach pendants to physically guide the massive robotic arms from point to point, recording the exact coordinates. The drawback is that the robot must be taken offline to be programmed. In a factory, halting the assembly line to teach a robot a new path means hemorrhaging money through downtime. To avoid halting production, factories use offline CAD simulation software. Engineers can map out the next task, calculate the paths, and write the code entirely in a virtual environment, while the physical robot keeps working. But virtual perfection rarely matches physical reality. Minor sensor noise or tiny deviations in how a clamp is bolted to the floor create a sim-to-real gap. The offline code always requires manual tweaking once it reaches the factory floor. In the industrial stack, algorithmic elegance takes a backseat. The defining metrics are minimizing downtime and ensuring the machine can repeat a highly accurate physical motion indefinitely. Attempting to learn this entire stack at once will burn you out. You have to pick your target. This decision tree maps out the paths. The choice comes down to what exactly you are trying to build. If your goal is to make robots smart, processing vision, navigating dynamic rooms, or integrating large language models, your path is Python and ROS. If you want to define exactly how a robot balances, calculating instantaneous motor torques to keep it upright, you need the absolute control of C and C++. If you are automating a factory to maximize uptime and push thousands of parts down an assembly line, you need to learn teach pendants and offline CAD. Successful roboticists don't try to code every layer from scratch. They pick the single layer that solves their problem, master it, and rely on middleware to handle the rest. Defining your desired outcome before you write your first line of code is how you actually get a robot to move.